Hi guys, welcome back to my mathematics tutorial. My name is Peter C. Doppler Jr., math instructor at the University of Liberia and your math tutor. So in my today's lecture, I will be discussing trigonometric, and under trigonometry, we'll be looking at the derivation of the Pythagorean identities. In previous video, we derived the fundamental Pythagorean identity, which was cos square theta plus sine square theta equals to 1. So in the previous video, so you can just check the previous videos, we derived this identity using the red triangle. Now in this video, we want to derive several other identities or several other related Pythagorean identities using just this identity. So let's start. So we derive maybe up to 10, 15 sets of different identities from this identity. So the first one would say, what if we have a case that we want to solve for only cos squared theta? So we know that if we want to solve for cos squared theta, so let's just call this identity 1. So we want to solve for cos squared theta. It means this sine squared theta, we must send it across the equal sign. So across here is already 1. So if this is going across, it becomes minus sine squared theta. So this identity is identity number 2. So what if from this same identity we want to solve for cos? Instead of saying, we're using the square now, we don't want the square to be there any longer. We just want to solve for cos of theta. So from this one, we can take the square root on both sides. So we say cos squared theta equals the root of 1 minus sine squared theta. So this root will cancel these two. We will now be left with cos of theta is equal to the root of 1 minus sine squared theta. So we call this identity number 3. Now what if from this identity we want to solve for sine squared theta? So we have sine squared theta. So since we want to solve for this one, it means only this sine squared theta must be on one side of the equation. So cos squared theta, we send it across the equal sign, and it will be minus cos squared theta. So we call this identity number 4. What if, like we did in this case, we only want to solve for sine of theta? So it means we must take the square root on both sides of this equation. So we take the square root on both sides, 1 minus cos squared theta. So this 2 now we cancel the square root. We have sine of theta to just be equal to 1 minus cos squared theta. So we call this equation number 5. Now, so we've derived several other identities just from this one. So we have now derived additional 4 identities. Now, what if we want to bring in identity for tangent, for cotangent, for secant, and for cosecant? What if we want identity for those 4 trigonometric functions? Now we bring this original trigonometric identity down, plus sine squared theta equals to 1. Now, let's derive identity for the first one, tangent. So we know that tangent of an angle, we told you in the previous video that tangent is equal to sine of theta all over cos of theta. So since we need tangent here, it means cos of theta must be divided in all of the terms. So in this term, we say cos. Now since each of them is squared, so we say cos squared theta, and cos squared theta. So cos squared theta divided by cos squared theta is just 1. Now sine of theta divided by sine of theta is just like you have sine of theta divided by cos of theta, all raised to the second power, because the both of them, they are square. So if you rewrite it like this, you have tangent raised to the second power. So this is just plus tangent square theta. And we also told you in our previous video that secant of theta is equal to 1 over cos of theta, and cosecant of theta is equal to 1 over sine of theta, and that of cot of theta is equal to cos of theta divided by sine of theta. So we need these important trigonometric identities. So 1 over cos, now this is cos square. So if you just rewrite that 1 over cos of theta as 1 over cos of theta all square, because we can square this 1. 1 square is 1, so it makes no difference. So this entire expression in here now is just secant of theta. So it is secant square theta. So this is identity number 6. So from this new identity that we have derived, from this new identity, this number 6, we can derive several other identities like we did for this first identity. So in this identity, we can decide to solve for 1, like we solve for cos square theta, sine square theta, cos of theta. So we can decide to solve for 1. So if we solve for 1 in this identity, it means 1 must be on one side of the equation, and we send the expressions on the other side. So it's secant square theta, and then this tangent go across, it becomes minus tangent square theta. So this is also identity number 7. So also we want to say, let's solve for tangent square theta. So we can say tangent square theta equals, now on this side we have secant square theta. Then this 1, we can send the 1 across, it becomes minus 1. So we can call this identity number 8. What if we only want to solve for tangent, getting rid of the square on tangent? So we will have to take the square root on both sides. So we take the square root on this side as well. And then this now will lead us to tangent of theta to be equal to secant square theta minus 1. Now, you cannot say you are going to cancel this 2 on top of the secant, because there are 2 terms in here. If this was just secant square theta, you can get rid of the 2. So this is identity number 9. What if we further want to solve for just secant of theta, because we have secant square theta here, which is equal to 1 plus tangent square theta. So what if we just want to solve for secant theta? So we can take the square root on both sides. Secant square theta, we take the square root on this side, 1 plus tangent square theta. So this will cancel. You're left with secant of theta now to be equal to 1 plus tangent square theta. So this is identity number 10. Okay, now, so you have individually solved for secant square theta, secant of theta, tangent square theta, tangent of theta. You have solved for 1. Now let's move to another batch of the identities. What if we take, remember, we just found tangent and secant, right? So we divided all sides by cos, and we're able to get tangent and secant. So what if we want to get cotangent and cosecant? It means we must take the original identity, which is cos square theta plus sine square theta equals to 1. Since we now want to get cot, and we know that cot is equal to cos over sine, so we must divide all sides by sine of theta. So now it is squared because the numerators are all square terms. Sine square theta divided by sine square theta, like the way we did in this case. So cos squared theta divided by sin squared theta is just equals to cot square theta plus sin squared theta divided by sin squared theta is just equals to 1. And then 1 all over sin. So it's like we said 1. You can square 1. Sin is also square. So we can rewrite it as, since the both of them they are square terms, we can say 1 divided by sin of theta all square. So 1 over sin now is just equal to cosecant. So that becomes cosecant square theta. So this is identity number 11 because we have found cosecant square theta. What if we just want to solve for only cosecant? It means cosecant square theta equals to cot square theta plus 1. We can take the square root on both sides, and then this square root cancel this 2. So we will now have cosecant square theta to be equal to the root of cot square theta plus 1. So we can call this identity number 12. Then in this identity that we derived, in this new identity, since we now solve for cosecant square theta and also cosecant theta, we can now solve for cot square theta and cot of theta. Then we solve for 1. So cot of theta now, we can make cot square theta the subject by sending this 1 across. So we will have cosecant square theta minus 1. So we call this identity number 13. So what if we also want to solve for only cot? So it means we must take the square root on both sides. That is, we do the same on this side, CSC minus 1. So this 2 now will cancel. So cot of theta would just be the root of cosecant square theta minus 1. So we call this identity number 14. So the last one, we can also solve for 1. So we can send this term across. So it's like 1 equals, on this side we have CSE square theta. So if this cot is going across, it becomes minus cot square theta. So these identities can be used in simplifying trigonometric functions. These identities can be used in simplifying derivatives after you have differentiated and then you have a lot of trigonometric functions. You want to simplify them. You can use these identities in several other areas when it comes to simplifying or verifying trigonometric functions. So thanks ever so much for watching. See you in our next video where we are going to do the half angle identities, the double angles identities, and the rest of the other identities, some of a sum, some of a difference, and everything. So thanks ever so much. Please don't forget to subscribe to our channel and hit the bell so that you get alarm whenever we upload videos. Thank you.